I guess so. Many thanks, Sarah, for the invitation, and I mean, it's always such a pleasure to be here. I mean, always. That's my second time, but last time was such a pleasure that I was very happy to be invited again. And yes, so things are going to be quite flexible. I have, of course, some things in mind, and I'm going to detail what I suggested to tell you during those 4 times 2 hours. But one can easily adapt, one can change things. So do not hesitate to give me feedback. If you'd like me to explain things more in detail, I'm more than happy to do it. One can also schedule additional times if you wish, or shorten them if you wish to. But somehow the suggested plan could be to spend some time first on classical spin systems and then representations. So this is what I'd like to do today. Spins and loop representations. Then and I mean, there are several loop representations, as I will explain. I will explain mainly the one due to semantic and Euclid for tensor, but I will also briefly detail some others, kind of as well. And then I'll discuss. So for tomorrow, I intend to talk about quantum space and the loop representations too. And one aspect that turns out to be a fact, which is only in recent years, is that when you look at it, so basically you have a large domain, and here one has to take 3 dimensions or more, and you have the whole loops. We can look at the lengths of the loops, and everything will be set in a probabilistic tone. So we have probability distributions on loop configurations, and you can look at the length of the loops, and the joint distribution turns out to be a so-called Poisson-Ueltschi distribution. So then I'd like to explain. I mean, one possibility is that I explain this in some details, and in order to do this, I would give a proper introduction to this Poisson-Ueltschi distribution, which is a distribution for random partitions, and that would probably take us 2 hours. So this Poisson-Ueltschi distribution. So here it's really going to be purely probabilistic. There will be no statistical mechanics involved during those 2 hours. So that's what makes me a little bit hesitant for those who would like to do the statistical mechanics. But the idea would be to describe, to introduce properly this Poisson-Ueltschi distribution and give some properties and some characterization. And then there will be this, the last 2 hours will be spent in explaining how the 2 are linked. So relations, so 3D distribution, the Poisson-Ueltschi is relevant to spin systems. I'm a bit vague here, but the main point is that we have this classical and quantum spin systems. This gives rise to some loop models. Very different loop models, but nonetheless, models with loops and probability distributions on loops. And then there is this conjecture that the joint distribution should be a Poisson-Ueltschi distribution. And the question is, what can be proved? And as you will see, the conjectures is far more than what can be proved. But I will explain some relations, for instance, between Poisson-Ueltschi and symmetry breaking, some calculations on mean field systems. Okay, it's mean field, but also to explain, some heuristics behind that, and the heuristics amounts to taking the probability distributions on loop models and understand some kind of Monte Carlo procedure for the loop models, and make the link to some characterizations for the original. So what I would explain in those two hours. So this is what I'm going to do, unless anyone suggests otherwise. One aspect which I am very embarrassed to admit is that I'm very late in the preparations of these lectures. I am only prepared today, to tell the truth. For the purpose things, I'm confident that I can do it this afternoon. But I intend to write down some lecture notes. So by the end of the 2 weeks, I will have done. And also, since I'm very late, it means that I can be very flexible, because it's not that I have prepared everything and you should feel embarrassed to direct me otherwise. So no problem for instance, changing a little bit, or even drastic. All right, but by the way, do interrupt every time. Perhaps it's good to remind everybody, but even silly questions are usually welcomed by the rest of the audience, because it's a nice break, and sometimes even silly questions turn out to help find things. So, and good questions also encouraged, but never hesitate asking questions. All right, so today I'd like to introduce classical spin systems briefly. Actually, just basically give the setting, but a little bit of explanations, and then embark on one of the loop of notations, and just mention the existence of related ones. So let me continue here. I'm not sure why I have the number one. I like to discuss the n components. Classical spin system. And here we start with a lattice. Lattice or graph, it depends how we think about it. I mean, for me, it will always be a subset of Z. And I'm using this symbol as in the book of dynamic, suggesting it's a finite subset of ZP. And then basically at every site we're going to get the spin, which is a little vector with n components, and they're going to interact. And for the interactions, let's be quite general to start with, and we have coupling constants. And the coupling constants are indexed by the lattice sites. So I'm going to get those coupling constants J, and now we have plenty of indices. There is X, Y, and I. And X and Y are lattice sites. X, Y, and data. And I are for the components of the system, so it goes from 1 to capital N. So all right, so try to memorize this. That's a bit unpleasant, but it turns out to help the individual when deriving those representations. So, what I'm assuming is that these are symmetric things. This is equals to J, Y, X, I for all X, Y. What you should have in mind is that they depend on X and Y. Like for instance, there could be a fixed number if X and Y are nearest neighbors and 0 otherwise. I have always this example in mind, but it's good to write this a bit more general. And that's where the spatial structure turns out to be important. And then we fix the unemployment. So the interactions between our spins are as follows. So H lambda has a spin configuration 5. And perhaps I should say what phi is. So phi we have a vector at every side. So and the vector has n components. So I'm going to write this like that. It's a 5xi with x in lambda, I with 1 to n. Okay? So then okay, you can rewrite this. Each 5x is an n component vector, or we have different numbers that are this. And the Hamiltonian is as follows. It's going to be minus, let's put the 1/2 over here, and we sum I equals 1 to n for each component. And then we take the inner product between the vector, yes, by I, j I, by I. This is the inner product in number. That also means that this is minus 1/2, and we sum I equals 1 to n. And we sum x, y in number. We have this j, x, y, I, and by x, I, by y. Okay, but let me say that this is also called the spin configuration. And this is the interaction. I hope things are kind of natural. I mean, there are different ways of writing this. And you can also sum over x and y. Now, if all the j's don't depend on I, which is a very interesting case for sure, you just get the unit product between the two vectors over here. But we can be a little bit more general and introduce it this way. And also here I'm using this kind of unit product. So that's another unit product. I mean, you have a natural unit product between vectors. So it's a unit product on Rn. But we can also introduce a unit product over functions indexed by x, I mean functions of lambda. And that's what it is meant over here. Okay? It's good to use identification. Is it kind of clear? I mean, the picture for those who are not too familiar, we have the lattice. And let me somehow perhaps write the two-component system. At every side, you have a little vector. And it has two components, so you can all still write it in this plane. And then you have these kind of interactions like that. So when you have all these vectors, h gives you a number, and this function is written here. And then this allows you to define the option function and the measure on configurations. So the so-called partition function is that lambda, and this is the integral over all R n lambda. So we integrate over all the spin configurations. And here we're going to put exponential minus h lambda pi. That's the x factor. And then we take the product of all sides. Now we put some function g over here, which depends on pi x squared. So we know to the square, d pi x. And here you get so this is the Warwick measure on R. Okay, so I assume you all have some, at least some vague understanding. I mean, nice idea of classical, sorry, subtle mechanics. And a partition function means that you integrate over all degrees of freedom with an exponential minus beta h, except that there is no beta. And the interaction means that the integration is that we integrate over all these vectors. Now we can put something which depends only on the Euclidean norm here, and we have this. I'm going to remind some special cases here and some properties. So let me perhaps define, and then I'll explain the basic things. And this function g, so g is the function from R plus to R plus. So that's going to be a first measure. And I'm going to split it, but it's a nice function. So, which means that here one has to do it in the physics way. We have a joke setting, and the important thing is that there are plenty of interesting, relevant examples. We should not do it in the mathematical way, which is to try to look at those counterexamples for the setting. That's not helpful. Think of a lot of very interesting examples. If the theory works sometimes, one is happy in physics. So I'm not going to dwell too much on this notion of nice. The thing is that I mean, as we will see, the derivation of the loop representations will assume that this is a smooth function, and then we apply it to it, right? Well, one has to justify this, but we'll see that later. Anyway, this allows to get a quantity measure on the spin configuration, which means on R and lambda. I mean, on all those vectors that are inside. And let's write it as, for instance, mu d phi. And it's going to be 1 over the partition function. And exponential minus h lambda phi. And then we take the product over all sides. It's here phi x squared d phi x. Okay? That's the probability distribution that we are interested in finite volume. And I'm also going to introduce the correlation function. Let's write this as for covariance. Let's write this as g lambda x y. Let me put also a superscript I here. So again, that's not the power, that's index. And by definition, this is the expectation with respect to this probability measure here. Phi xi, phi yi. And this means, in other words, I mean, just to clarify, we integrate over all the spin configurations and lambda. And we have phi x component I, phi y component I also, mu lambda d phi. All right, so basically the setting is here. Now let me review a few special cases and a few basic properties which have been established or just unexpected. Yes. And here, special cases. Because it covers a lot of interesting cases. The first one, suppose you take this function g, the phi x squared. So this time start with the smooth functions, like exponential minus 1/2, let's put 1/2, m phi x squared. That's quite a natural choice. then the phi x are of course kind of, I mean, cannot be 2 to the power of 0. And in this case, I mean, you can see, I mean, with the h having this form, you put the g, I mean, it actually gives a diagonal, adds a diagonal term here. You can rewrite this as a product. And here you have the so-called Gaussian free field. Gaussian field. Or the discrete Gaussian free field. I mean, you can also define everything in the continuum, which is actually a tricky thing to do. But here you get a discrete free field. So actually, yeah, this is what I should say. Here, and I should write with an S, with mass m not equal to 0. So this m is called the mass in this context. And in fact, we have fields with an S over here. The S means that we have actually n distinct Gaussian free fields, and they are all independent in this case. The reason is that you can check, and the h over the Hamiltonian is the sum over all components. If you write g over here, it's like exponential of the sum. So everything is like a product of independent Gaussian free fields. So in fact, in this case, the n component goes off to be very relevant. Okay, so that's a special case. I mean, more interesting, you have this like pi-4 model, where the g has, yeah, I guess I like this better. When you have a combination of pi-4 and pi square, and there are lots of other things. But the other case that I like to mention is when you take g of pi square x square equals actually a Dirac at 1. Delta pi x square minus 1. So to tell the truth, I'm a bit confused about what it means because we have a product of integrals of Dirac. But let's not worry too much. Basically, if this nice function g, I mean, imagine that we take a unit where it concentrates on the unit ball with, I mean, sorry, a dimension n minus 1. Then it means basically that when you do this integration here, you should integrate for pi over Sn minus 1. So the unit sphere minus 1 dimension. Okay, and then you have plenty of interesting examples. Mainly, if you take n equals 1, the one component system, so integrating over the unit ball, I mean, you have just one component, the square should be 1. So the component has to be plus or minus 1, and this is the easy model. So as a special case, one component with a suitable G, that's easy. This is the easy interaction here. So we already know the easy model. And equals 2. This is also a famous model, which is called XY, or classical or rotator model. N equals 3 is usually called the Heisenberg, classical Heisenberg model. And there is no reason to stop at N equals 3. It's not mathematically, but physically perhaps. So these are the special cases that are all included in this differential setting. Also, the standard classical XY or classical Heisenberg will have the same gapping constant for all directions. But that's, of course, allowed in this setting. We just don't assume it will be solved. Any questions so far? Then let me briefly describe what is kind of expected for the behavior. Okay, I just go and functions here. And so expected and sometimes proved it. So but let me just write expected. And here I'm going to assume that the GSSIs are larger to 0, the so-called paramagnetic interactions, and think of most coupling constants to be like zeros like this. It goes a bit beyond that. Then the point is that we integrate over the speeds. This thing, the function g does not give you any information about the orientations, or only about the magnitude of the speeds. And think also the g to be like for, I mean, this zero at 1. So the speeds are at no 1. Now everything is weighted by this exponential minus h. The h, and now we have plenty of signs which may be confusing for mathematicians, but for physicists they are very natural. This encourages low energy configurations. And low energy configurations, when we have this minus and the product of spins, so we get the lowest number when the spins are aligned. So one should remember that this weight over here encourages spins to be aligned. So when the spins are essentially aligned, you get the higher weight than when they are not. So when you think about this, the measure tries to encourage neighboring spins to be kind of aligned, but it's not necessary. So you are allowed to get something different. Every time you do it, you get something here, which is I mean the h is more, exponential minus h is less. So in terms of probability theory, we have plenty of random variables at every side, and we have periodic boundary conditions, so perhaps the distributions are, let's say, identical, but they are by no means independent. And the dependency turns out, I mean, immediately at least, hand all of them to point in the same direction. Then the question is, when we have very large system, whether we expect some kind of long-range operations to build the system. Then, so what is expected is that if the coupling constants are small, I'm going to be a bit vague. I mean, one way is to say that they are all equal, I mean, for nearest neighbors. Then we put you multiply everything by beta, that would be the natural thing, and here that means really beta small. So beta small is high temperature, it's not disordered. So what is expected is that this covariance GXY has exponential decay. So if that's equal to a constant, exponential minus another constant, and the distance between distance say between the two sides. So things are not independent, but asymptotically they are. In a large system, the covariance goes to 0 very fast. By the way, I call this covariance when you can think perhaps it's more like a moment. So the covariance, you should subtract the product of expectations. It should be clear that the expectation of a single one is 0. That makes symmetry. There is a symmetry between configurations pointing in one direction, and you revert all the directions, you get exactly the same measure. So the expectation of phi xi, I mean, just one of phi x is 0. So this is the product. If it's not clear, we'll do this as an exercise. So that's what is expected, but actually not to prove. But we have exponential decay at low temperature. More interesting is what happens when the Kaplan constants are large, meaning that H is much larger, and this weight has more effect. And everything depends on the dimension. So this I should mention all D. Remember that D is the spatial dimension. Capital M is the dimension of the spin space. Then if you take one dimension, that turns out not to be too interesting. This G lambda I, right, so we have a lambda over here. So mathematically, this statement is obvious, of course, because you have just finitely many terms over here. If you take a constant large enough, that works. But what is saying is that the capital C and little c do not depend on the inside of the system. That's where the claim has absolutely non-trivial value. So dimension 1, this thing always has exponential decay. C exponential minus C x minus y. No matter the Kaplan constant. Or, I mean, to be precise, you fix the Kaplan constant and you can find the C and C which don't depend on the size of the number. I'll try to write this a bit better. But the point is that when you have finite range interactions in one dimension, in classical systems, nothing interesting happens. It turns out to be absolutely non-trivial when the J's are allowed to decay slowly, like with power law, with low power. And you have very interesting regimes where everything makes sense from the substance mechanics perspective, so that the energy exists and things like that. And the strength of the Kaplan constants turn out to be relevant space conditions. So I don't want to dismiss one dimension support, but for finite range interactions, yes, nothing happens. Now, everything is much more interesting in high dimensions. Equals 2. Then things actually depend on the number of components. If you take n equals 1, which is easy, then you have a g lambda of xy is actually here I can put component 1. It's the only one we have. So this can be proved to be positive, greater than 0, and this constant C again does not depend on the size of the system. If the jxy 1 are large enough. So, or in other words, if beta is large. So beta is large, it's what was first by bias, but you have long range order, and one way to write it is that this two-point function is bounded uniformly away from 0. And this is in contrast to this situation. So then you have a phase transitions when you vary the strength of the constant. You go from exponential decay to the uniform Laurent. So it also means that if this weight, I mean, which encourages the spins, I mean, you put like a beta with beta large, so you really actually quite discourage any change. And this is the one component, so we have only plus and minus. Then indeed at low temperatures, everything is mainly plus or mainly minus. Is it kind of clear? So if you have any seen something about easing, I'm just explaining what happens to easing. Then in n equals 2, things turn out to be very interesting. So I should precise that now I also have in mind that actually almost coupling constants do not depend on height. That's what I wanted to explain now. If I depend on I, then we are actually using regime. So suppose that so we have two coupling constants that they are the same. I mean, two components interacting in the same way, and then it turns out that there is a so-called DKT or Ueltschi. So it's always condition. And it means that, well, I mean, this is still true, that for small interactions, you have exponential decay, but when you have large and large interactions, at some point you stop having exponential decay and you have parallel decay. So you still have decay. This function still goes to 0 when x and y both become large, and this goes to 0 uniform in the cyclic system. But you have actually a parallel decay at low temperatures. That's something that physicists are extremely interested about, with, and also something which turns out to have been proved by Ueltschi and Spencer. I mean, the 80s, and something which has been reproved quite recently by two groups of people. One is Hazelman, Shapiro, Aren, and Pered, and another one is Warwick and Martin Bliss. And I'll try to comment a little bit about this latter work, because all those two works about proving this decay transition are largely based on those root models. So this is, I mean, first the paper of Ueltschi and Spencer was pretty remarkable, and for decades nobody managed to actually find a better way, a simpler way to do it. And only recently, the paper was, I think, appeared just last year, that there was somehow a more streamlined way to do it. And now that was free. Well, in this case, the decay transition is not expected, and what is expected is that there is always exponential decay. This is also known as Polyakhov's conjecture. And this is something not proved, and even this conjecture is not universally accepted by physicists. Still a bit mysterious. So that could be one of the very nice things to anyone possible to prove this thing. Any ideas? But this is definitely something quite difficult to prove. And right, so that's what is expected. So this is for dimension 2. Then dimension 3, or larger equals to 3, when you expect actually a phase transition to a phase where all the spins align. So then what is expected is that it's G lambda I, y, is greater than C greater than 0. If J by I are large. And this was proved by reflection positivity. I mean, using reflection positivity by Ueltschi and Spencer in 1976. So in a nutshell, this is what one can say. So sometimes spins align, sometimes they never align, like in these situations with the decay transition. Sorry, I should say here. But you still have this very interesting change of behavior from exponential decay, so very short range iterations, to something with parallel decay. And really, it is expected that this has consequences for what is I mean, perhaps not quite directly, because this two-dimensional system don't exactly exist as such. But there are quasi-2D systems and things like that. So also knowing that the 2D system has only slow decay iterations is expected to have consequences for the behavior that you see. So, and mathematically, it's nice that you have all these different behaviors, and of course the challenge is to try to put some of them. And some of them can be established rigorously. Some, especially with projectors conjecture, have resisted all attempts to proofs or ever since it was formulated. Any question?
Just have curiosity.
Yes.
About the polygon conjecture. What does I don't know, if there is some experimental evidence of numerical simulations that show us the direction of what does it mean to have this?
So I mean, experimentally, I don't think we can really see it, because that would mean having a genuine system of spins, which is 2 dimensions, which is very hard to do, and then we check that you have this exponential number. Not sure how you can do it. Now, numerically, yes, there are experiments and they are compatible, but it's really hard to, I mean, numerically to get really exponential decay. It's one thing to establish the absence of magnetization. I mean, you average all the spins and then see whether the total spin is like the size of the system or it's something much smaller. But really to look at the 2-point function and how it changes when you change the sites is something really very difficult to get molecular estimates. You need really very precise values to see the function, and when you see the function going to 0, you see it going to 0, and now to distinguish between exponential and parallel, so the systems cannot be so large. So as far as I know, it's numerical simulations are compatible, but they are not completely proven. No, I'm not an expert on this, but anyway, when I say something, if anyone has more information than I do, I don't hesitate to comply. So yeah, as a result, I mean, this conjecture is kind of solid. Most people accept it, as I understand. But it's not one of these things which are completely solid, but it's absolutely impossible to think otherwise. So perhaps there will be at some point a little bit of a surprise. This must be checked. All right. So any questions? Yes.
I understand what did about the Berezovsky in the other transition. What did Eisenhower and the rest prove?
Yes. So this is actually n equals 2, so 2 components. Now it's not quite this system, but it's the so-called V-line system, which is very closely associated to the classical XY. On the other hand, the Marchand-Lewis and the student, it's really the XY system. And they prove that the low bound for the decay operations, the low bound being the parallel with parallel decay. And that's a difficult thing, because the fact that 2-point function decays at least as fast as parallel was proved first by McBride and Spencer, so not bound was known, which works for all space components. So in 2 dimensions, it's actually proved that the 2-point function always goes to 0. So this behavior does not happen in 2 dimensions for sure. And the upper bound turned out to have the right shape, but the exponent is like a constant over beta, that's what is expected. And this was proved by Warwick Spencer. The difficult thing, which was proved first by Warwick Spencer, is the lower bound. But indeed, for beta large, you have no more than exponential power law between. So this is what those two groups managed to reprove. Obtain the lower bound. Yeah, other questions? Maybe it's time for right time for break, yeah, because next thing is to introduce the loop models, and we'll see what I managed to do.
Yeah. We can start in 10 minutes.
Yeah.
Thank you.
We start. Okay, so since we forgot to erase let us remind the setting. I guess the oldest stage is over here. So I hope this situation is clear. I mean, we have this classical spin, so an M component vector at every side. That's the partition function, and this is the measure. So everything is weighted on with this exponential minus h. The partition function makes it a probability distribution. And something of interest is the covariance between two components of the vector or the variation function. And then the special cases here. So somehow these three cases are the ones which are mainly interesting. But it's good to have this general function G, especially because it turns out that for the loop derivations, one is going to dilute the Fourier transform of this function. And the easiest is to imagine that the G is a smooth function. Once one has the loop representations for finite systems, there should be no problems taking the, I mean, if we have a sequence of functions G, we can somehow move it to a zero. And otherwise here there was this brief descriptions of what is expected in different contexts. So everything depends, as you see, on both dimensions we have, the spatial dimension D and the dimension that means in space capital M. That's right. So now I'm going to write all this and introduce the loop representation, and then I will state the result, which is that, for instance, this partition function here, which is written in terms of spins, can be written as a partition functions for loops, and also something about this grid function, but we also have some equivalents. There is another aspect that it's not worth mentioning. Today I'm discussing classical spins. Tomorrow I will discuss quantum spins, and there will be basically no overlap with what we have seen over here. And when I discuss the Poisson-Déruchette distribution, there will be also no overlap with what we have seen before. So it's only the very last one that we put things together. But it means that if you are completely lost at the end of the 2 hours, you still have a chance to catch up for the first few minutes for the next time, because we started it. Oh, I can erase. So as I mentioned, there are several ways of introducing loop representations or some kind of spatial objects for spin systems. The one that I'm going to explain today, next section. This is the one into Siemens-Zig, and also with this Ueltschi and Spencer. So Siemens-Zig did it in the context of field theory,
And Ueltschi for Spencer were mainly looking at the spin systems. And I cannot remember what they were looking at in terms of this, but I mean, the idea was to get the result about spin systems, and they used this for notation. So this is why everything is named after them as well. So the definitions to start with, and we're going to introduce paths and loops. So first, paths. We write this as gamma, and this is a sequence of sides, x1 up to xk, with xi in lambda, the subset of ZB. We always assume that xi plus 1 is not equal to xi, so we have a sequence of sides not repeating the same site consecutively, but the loop can come back. And then we also give an extra information which we could color. A color I equals 1 to m. So the capital M, I mean, as you will see, is the same M as for the dimensions of space. And a loop is something similar. So we also write this as gamma. It's also x1 up to xk, and k varies. We also have that xi is lambda. Xi plus 1 is not equal to xi. And now we have an additional thing, which is that the same loop can be written in different ways. We can look at the cyclic permutations of these sides, and we get the same thing. So one way to say is that if you take the sequence x2 up to xk, and then you put x1 back, this represents exactly the same loop as this one. So this is identified with x1 up to xk. And of course, you can repeat this procedure. So any cyclic permutations of both sides give rise to the same loop exactly. So, and we also have a column. So what does it mean? Perhaps I can illustrate this over here. So we look at the sides, and we have this notion of a path. So a path starts somewhere. So this will be x1, and then let me draw things with only nearest neighbors, but that's not necessary restrictions. And we go somewhere. We are allowed to cross back. We can use it again, and this could be like xk. So this would be like a path x1, xk. I don't know what k is in this case. Again, and what about the loop? And here let me draw a loop. So we start over here, while I'm doing the same with the variations. And we do this thing. Maybe we repeat over here. And we need to, for the loop, we need to end up at, I mean, we kind of close it. Some, I mean, you need that stuff. So this is the loop. And I mean, when one looks at this thing, I mean, whether it closes or not, it looks irrelevant. But let me introduce weights for these objects, and you will see why you do this and why it was passed like that. So the weight is a positive number associated at each path and each loop, and it's as follows. So let's write this as omega, or the W, but let's call it omega. So for me, it's always omega, I don't know why. And we have a slightly different weight for paths and for loops. So if it's a path, you take it as a product. I want from 1 to k. And I should say that the k is the length. Length. Gamma equals k. So this k over here is going to be the length of the path, and also the length of the loop. So
Maybe
yes,
sorry, probably I'm confused about the notation. We are implying here that the length of the path is always less than 10.
no, but the length is obviously large.
We are considering n different colors.
Yes, sorry, the color is just an extra information we give to the loop. So what is a loop? It's a sequence of sites, and then we give an extra label, which is a color. I forgot to mention giving the examples. But the color has no effect here. It just happens that for the loop representations, each loop will have a different color. Actually, the way that I'm going to put the color here. The weight of the loop depends on its color.
So the two labels over there are not the same.
I think it's because you use I twice.
Oh, that's right. Yes. No, it's not. Let me put the J over here. J. Yeah. Thanks for pointing out. I should not use the same label all the time. Right.
And gamma does not have any label telling the color? No.
Well, when we say again, yes, it should. But it's not elegant to put it. So, but yes, I mean, when you see gamma, there should be in addition. I mean, you have this and you have the color, which I'm going to call I of gamma. So yes, so do ask most questions because the presentation is confusing. Better to clarify. Now the color is going to appear here. So we take the product one, or maybe here is with the length of the parts, and we take this coupling constant that we had before with xj. Okay, here I'm going to put j. xj plus 1. And here we put, you remember we had this coupling constants with this extra index. So we put the color loop. And this is gamma into path. Okay, so we take and put it gamma minus 1. Well, it's we go x1, x2, x2, x3, and we stop x gamma minus 1, x gamma. All right. So this is the way of the paths, and I mean we use the same coupling constant as we had for spins. It's unsurprising. And now for loops, it's kind of similar, except that here I'm going to put an extra factor 2 over r of gamma, and it's kind of this. And then we take the product, and j equals 1. This time we go to gamma, that's correct. J, xj, j plus 1. It's I of gamma, but again the color. If gamma is a loop. So you see that here we go one more. And of course, x when j is gamma, gamma plus 1 has to be understood as 1. So we have all these weights, including the one for the endpoint and back to the first one. So that's why it is zero. Now, what is the, I mean, the 1/2, it's not important, but just happens to be there for the loop representation. What is this R of gamma? R of gamma is the number of times the loop repeats itself. So it perhaps feels a bit unnatural, but in fact, turns out to be present here and there. The orders no such. So here, R of gamma is the number of times the loop repeats itself. Probably don't understand what I mean by this. This means sorry? No, it's not a good guess, but no. This means the following thing. Suppose you have a loop which goes this thing, and then again exactly repeats itself and stops here. So then this R gamma would be 2. For most of the loops, even those with some intersections, R gamma is just 1. But if it's such that we can take a smaller set of x's and then you just repeat itself several times, then the R gamma is this number. Okay? So why it's there? Well, it turns out to be very relevant when we do the expansion, and we have to put this in the way. So now we have a notion of loops and sequences of sites and a weight, and then we are going to introduce a sustained mechanics model with these loops. Also, you see why I insisted on the nearest neighbors only. The Captain constants are like non-zero only on nearest neighbors. Then loops with positive weights necessarily have nearest neighbors. And same with us. Okay, so the idea now is that we are going to get a gas of loops with those weights. Loops are going to interact with one another. And the interactions turn out to be quite simple, or at least not as complicated as we may imagine. They only depend on how many times loops go through a given site. So for this, we have a notion of local time, sometimes it's called local time. The name has nothing, refers to various different interpretations of these things. I'm not going to dwell on that. That's the following thing. So X is the site, I is the color from 1 to n, and here we look at the number of times a loop of color I goes through the site X. So let me write this. So this is the number of J equals 1 up to gamma, such that X J is equal to X. And if gamma has color, the right color and 0 colors. Okay, so it's not something very abstract. You take a site over here, it's called this X, and then you have this loop, the green loop, and you look at how many times the loop goes through this site. So for instance, with this loop, I mean, when we have to be this point over here for this path would be 1. Okay. So this is the so-called local time. So it records how many times the loop crosses a given site. If the loop does not pass through this site, then that's 0. And And also this has to do much with the color. So when we have this, we can also introduce the local time for several groups. So when we have gamma 1, gamma, let's say L, that's going to be true. And here, the local times associated with many loops, we just sum all those local times for each loop. So we sum j equals 1 to L and n I of gamma j using the previous definition.
Why do you define the local time on the loops? Not on
Actually, loops at us. So,
okay.
yeah. And again, and now I can claim the theorem which relates the loop system and the spin system. So what do I write here?
So there is dependence on X in this Ni gamma 1.
Sorry?
There is a dependence on X and I X gamma 1.
Yes, thank you. Yeah, sure. Yeah, so for each X we have this. Yeah. Sana, how can
So
write
is,
this down?
I swear there is not enough space, right? Over there.
No, I mean I could write it here and here.
Yeah.
So that's right. So here, and this is the semantic reference for each chapter. And we have two parts. So part A is that if you take the partition function, so this is the one with the classical spins that we saw before. So you can write it the following way. This is all right, it's convenient to put the 2 pi 1/2 lambda n. And then you sum over loops. So the number of loops, that's okay. One of the k factorials will be summed over gamma 1, gamma k. So these are loops. We have the weights. Omega gamma 1, omega gamma k. So you see the partial function is the sum of those loops, and now the loops interact. And okay, and then let's write the interactions as exponential minus some kind of energy of all those loops. Gamma 1, gamma k. For now. But then in addition, where this here, where this u of gamma 1, gamma k. So a priori, I mean, interactions between loop could be something awfully complicated. It turns out that it only depends on the local times. And this is given by the sum over all sides. And sum we sum over all sides, and we have some function b, which depends on x, and it depends on all this nx I. Gamma 1, gamma k. So it looks complicated, but not really. And I runs from 1 to n. Okay, so when you have loops, I mean these loops, you see what they are. So when you say that you have a function which assigns energy to those loops, a priori could depend on lots of things, on the shape, on plenty of things. But in fact, it depends. I mean, it's a sum over each side. At each side, it just depends on the total local times. So the interactions given by this side, I mean, it's enough to know that you go through this twice. Okay, but I split this color. I mean, we have different colors, and we have to get the information for each color. And now, I mean, for instance, if you know that the local time is 2, like this one, we have a same loop which occurs twice here. But you could also have another loop over here. The local time is also 2 over here because of 2 loops. We get the same interaction. So it's only the total local time which matters. So the variety of function V to be defined later, such that the interactions of all those loops only involve the number of times, I mean, for each side, we will just look at how many times we go through. So this is what is very nice about this loop representation. The fact that we have loops connected with gapping constants is not too surprising. The fact that the interactions are only with local times is okay. So now I still have a good half an hour. I will probably overlap a little. I mean, it's go a little bit beyond to explanation here. What I like to do is to sorry, I forgot the second part of the theorem, which is about the Green's function. Second part, the Green's function, operation function, or covariance is like this G. So let me write just the GXY. Sorry, I like to use it. So you can write it in terms of those loops. It's like 1 over the partition function 2 by 1/2 lambda n. Now, what do we have? We sum over a gamma, which is a path, this time x equals to y. This is a path. And the color is I, the same I as the I over here. We have the weight of this gamma, and then we have the sum over k also equals to 0. We sum over lots of other roots. Sorry, 1 over k factorial. We sum k gamma 1 gamma k. We have the omega gamma 1 omega gamma k. So exactly as before, and then everything interacts with everything. So we have an exponential minus u, and the u has all those loops and the paths. And here we have loops. And here we have the gamma, that's it, and then we have gamma 1, gamma k. So this is the representation for correlations. They are given in terms of the paths from x to y, under the right color, with the weight. And then we have these Gaussian loops, and everything interacts with everything else. Okay? So this is the loop representation. And now I'd like to attempt to prove it. So to prove it, we need some facts. I mean, basically, some formula for Gaussian integration. And there is a curious function for which we need a Fourier transform. Let me just go over proof. We need it. And let me just list those properties. Gaussian integral. And here we can formulate it this way. So if capital A is a finite matrix, so let's call it, let's say it's L times L matrix. Then we have the following thing. To integrate over RL, exponential minus 1/2 x ax dx1 DXL. So we work in L dimensional space. We integrate over this L real numbers, and everything is weighted by the exponential minus 1/2 x(ax). So x is vector x1 xl, and that's the usual matrix multiplication and the usual product in Rn. So this can be written as 5 L over 2, and then you have the determinant of A minus 1/2. Again, for L equals 1, and then it's you can quite believe it. If A is a diagonal matrix, it makes also sense, and then it's basically a change of variables. Like that. In terms of moments, we also have a formula which is supposed to integrate over here, and we have xi xj over here, exponential minus 1/2 x(ax). It's 1 xl. Then this turns out to be 5 L over 2 is determinant of A minus 1/2, and we also have A at I. So here let's assume that the matrix A is invertible. I mean, if it's not, the determinant is 0, and already this formula doesn't make sense. Okay, so these are facts which I'm going to use. Next, let's do something about Fourier transform. So conventions about the Fourier transform. Everybody has its favorite Fourier transform. And I'm going to do you the following thing, which is that the Fourier transform of the function on R. So I'm using A for the Fourier variable. So it's going to be 1 over 2 pi the integral on R, so from minus infinity to infinity, exponential minus IAS G of S, yes. And then you have the inverse Fourier transform, which allows that G of S is equal to the integral from minus infinity to infinity, exponential plus IAS G hat plus A. Okay. And you know that it works for plenty of functions. I will assume that it always makes sense for all functions that we have. Here, there is absolutely no need to worry. I mean, in case you worry, you quite long to do it. Even if we do not have, we start with a nice function g, you can always approximate in the finite domain by a nice function g, I mean like Schwarz. And then all those formula work. And at the end, when you get the loop of notations, you take the limit, and everything is fine. So indeed, the function g can easily be a distribution. Then we need a curious function, and so what do I have to go into the number? So let and now comes the curious function. I don't expect you to give a lot of sense to it. So the function f, s is a real number, b is an integer here. So it's going to be 2 pi over gamma of b, 2 to the power b. Then the indicator of the characteristic function that we are in the negative numbers. That's yeah, right. Analysis with the 1 for this. Then we have, so the function is all non-zero only for negative s. Then we get minus s to the power v minus 1, exponential minus 1/2 of js. And I'm a bit confused. So j is strictly positive. But it has minus 1/2. Okay, and we somebody else. I can't remember whether I put it correctly. Okay, let's not worry too much. So this is the function, and then as it turns out, the Fourier transform of this function is more or less like 1 over something with the sort of power. So after b of a, you can check is equal to minus j minus 2ia to the power minus b. So this is a nice function because j is real and a is also real. So this is fine. And then note some properties over there. And of course I have to check this slides. So if you take f up of b, a, we might have f up of b prime, a. So then you have b and b prime over here. So of course we get b plus b prime. So we have this important f up b plus b prime. And in terms of the original function, I mean, when you have two functions whose Fourier transform is related to its multiplication, then the original function is a convolution. So then we have that f of b convoluted with f of b prime. So we take this on x, and you get with my definitions of the Fourier transform, there is a 2 pi over here, and f of b plus b prime. So we have these kind of properties over there. So I don't expect you to know where this comes from, but and also most properties are or back as many things in analysis, but one can indeed calculate and check that this is correct. So now this is basically the kind of identities we need to do the expansion. The expansion is much more fun than those equations, I guess. So let me do the expansion, and you will see it's a very nice way of doing. So okay. On the theorem. And okay, so we start with the partial function. So we have the z of lambda. What is it? It's like the integral over r n lambda. So I'm going back to the spins now. We integrate over all spin variables. Let me write it this way. So we have a product over all x in lambda and the leg integrals. Then we have the exponential 1/2 with the sum I equals 1 to capital N. But something which can be written in terms of matrices, we have pi, pi here, pi I, and ji, pi I. And then what I have still not put is the product of this g of psi x squared. Remember, So this I'm going to use to write it in terms of Fourier. So then this is like integral over R of lambda because we have something for each side. Product over all x in lambda. Exponential of I, some Fourier mode or Fourier variable which depends on x, by x squared, g hat ax, and we have it ax. Okay, so if you just integrate this, you get actually g at pi squared, and that's what we had before. Itself, but the whole thing over here is like a product of the whole x over g of pi x squared. Okay, because we integrate, or we have depth integrals over here, but in fact everything factorizes, and we just get the g at pi squared for each x. So then that's exactly the Fourier transform. But the natural thing to do when we have two integrals is that we exchange the integrals, and so we write this as the integral over R lambda, so this thing over here, and we have some z which depends on all those a's, and product of x means lambda, g hat ax, ax, and of course the a is ax method. And I can write what the z is. The z is basically all the things which we have to get. So we integrate over all those things, and exactly. A is given by the integral over R n lambda, and then we have this exponential of this Gaussian term, 1/2 sum I equals 1 to capital N, and then we have pi. This pi I, this. Then this term is going to be, it has to be the ZA, and we can put it over here. We get JI plus 2IA by GI. It looks a bit messy, so carry d by x. X in lambda. So the new thing is that this term over here can be written as a Gaussian term. That's the subtle thing. Because we have a product over x, it's like the sum over x, and this is like a diagonal term in this expression here. So the JI is a lambda times lambda matrix. But A is a lambda vector. The vector can also be understood as a diagonal matrix. So here, in fact, it's really a diagonal matrix in this notation here. So if you take the A to be diagonal matrix, then this inner product means that the sum of the x and y. This term gives you exactly this term here. And the other term, the pi I, is what we already have here. Okay, so this is the idea that we write everything in terms of ZA and this product of G hat. The ZA is a Gaussian integral. So for given A, everything is Gaussian. And we can actually calculate its beta using the formula that we saw. And then we will still integrate over those modes. And those modes are going to give us the interactions in terms of its local times. Is it kind of okay? So let me continue. I can erase all those formula here. Yes. So then, with that end, so using the formula for Gaussian integration, we get 2 pi, and we have 1/2 lambda n. Then we have a product. I mean, in a sense, we have for each color I or each component I, we have a separate Gaussian integral. Product over I, and then we get the determinant of the matrix minus ji minus 2ia. And everything is to the power 1/2 minus 1/2. Okay. So I hope this is clear. So now we have to find a way to expand the determinant. And this is by expanding the determinant that we get the loops. How do we do that? So first, let us write this matrix over here, this minus ji minus 2ia. By the way, this I is of course not the same as this I. I is between 1 and n, and this I is the complex I. So in the notes, one will be italic and one will be Northern size. So let's write this as d, and we have this next I minus ki. And where d is the diagonal part and k is the rest. So di, so it's a matrix indexed by x and y is inside. So by definition, we call this is equal to minus delta xy, omega symbol. And then we have ji xx plus 2i ax. So this is the diagonal part of the matrix that we have over here, and ki is the diagonal part. I don't need to write it. So that's the diagonal. So then, now we start the expansion. We have that the determinant minus ji minus 2ia, and we have minus 1/2 is equal. Now the trick is to put I mean this we write as di ki. We put the di up front. I mean actually yeah, let's not worry about it. But I mean the diagonal elements we can think that they are non-zero. And so we write it the following way. That's like the determinant of the I only with minus 1/2. And then we have the determinant of the identity matrix minus e. Let me write I and minus 1. I hope it's understandable. ki. And we have minus 1/2 here. So this di minus 1 matrix di and the inverse. These things, I mean, determinant of the product is a product of determinant. So you can put this over here, the di and the di minus 1 cancel, and you get here di minus ki. Di minus. Oh yeah, right. We have this here. Sign square. So that's the first trick. This thing is going to be like the prefactor. What we are really going to work is expanding this term. So we say that this is the determinant of the I minus 1/2. And then a trick for calculating a determinant is to write it as the exponential of a trace. So we write this as exponential of minus 1/2 the trace of the log. I should trace of 1 minus the I power minus 1 AI. Okay, so trace of the log, trace means like the sum over all eigenvalues. So we have the sum of the log of eigenvalues, it's like the log of the product of eigenvalues, it's like the log of the determinant. And then we get the exponential of the log, which is just the big we started from. And of course, this minus 1/2, you can write this exponential, everything to the power minus 1/2. So I hope you agree that this for many matrices that's true. And now we're going to expand the log. So we say that this is like okay, let me put this again. And then we have the exponential 1/2 plus 1/2 indeed. Sum n not equals to 1. 1 over n, I'm extending the logarithm. And we have a trace of vi minus 1, ki, everything comes to the power n. So here I'm using the formula for log 1 minus x, which is minus the sum, you have the 1 over n, and this thing to the power n, and okay, and exchange the sum and the trace. And now you kind of recognize the loops perhaps, because we have a trace of the product. And the trace really means the sum of the sides, because we have matrices indexed like sides. Trace of the product using matrix properties, we get walks or loops. So the 1 over n, then we have a trace of this vi minus 1 ki to the n. How can we write this? Right, it's also like 1 over n. And now using the usual thing, we sum over the indices that we have in this space. And here we are going to get sides, so x1 up to xn. Like that. And we have di minus 1, x1. Then we have ki, x1, x2. So this is this thing with x1, x2. Now we have this thing x2, x3, which is going to give us di minus 1, x2, x2. Then ki, x2, x3. And we continue all the way to di minus 1, xn, x1. Oh, sorry, it's xn, xn. And the ki is xn, x1. Okay? So now we are getting the sum of the loops, in fact. And also this case, these are the octagonal things with the j's. So in fact, each of these cases is a j. So this is like ji between x1 and x2. So this part is exactly the weight of the loop. So we can write this as the sum over loops, gamma equals x1, x10. It's the loop. And the product, j equals 1 to n, ji, xj plus 1. So this is the thing coming from the i's. And then you also have the product. You can look at how many times we have these these and in the diagonal terms. So that the product of the x lambda, and we have this minus j I x x minus 2i ax. And the number of times this occurs is precisely this these local times. And gamma. I mean, gamma is a loop cover I. Okay, so we sum over x1, xn, and the sum over x1, xn is written as the sum of the loops. Now there is this thing about the loop, but we identify the loop and when we shift. So a given loop, I mean, you can start it here or you can start it at any time and you get exactly the same contribution. So at the same time here, we start on the x1 and xn, but the given loop appears precisely n times. I mean, if you look at exactly this sequence of things, sorry, if this is a loop, this appears over here when you start, you say that x1 is here, but if you say that x1 is this number here, you get exactly the same loop here, and you separate it here. But we divide over n, and this accounts for it. So n is the number of starting point. Now there is, so Jorgos knows that, there is a subtlety which actually escaped the bridges for each tensor they first wrote the paper, which is that when you have a loop which repeats itself, you have to be careful because the number of starting point is not 8, which is the length of the loop, but 4. And the 4 here is 8 over 2, and 2 is the number of times it repeats itself. So to make the combinatorics correct, you have to divide by this star gamma here. So now it's correct. And okay, I need to check these states. And then this is also like the sum of the gamma, gamma loop. I. And here we recognize 2 times the weight of the loop, because we have exactly this 1 over our gamma and the product over here, and the loop was 1 over 2 our gamma. So that's why we get 2. And then we still get this product of this minus j x x I minus b I a x to the power minus I x. Yeah. So now we are getting closer. I mean, with this we get that this expression here gives us actually it's a loop of size 10. Yeah, right. Gamma equals 10. So this is for the expansion of exactly what you have over here. The factor 2 is going to cancel with the 1/2 here, no worries. And we have the sum over n, meaning that we are going to sum over all loops of arbitrary size. And now we have the exponential of the sum of the loops. So this is like, I mean, the sum over k and then the sum over lots of loops. So that's how we get something quite close to over here. So we okay. that this product I equals 1 over capital N, and the determinant minus AI minus 2IA, and there is minus 1/2, is equal to the figures. So try to skip the 1 intermediate step. So if the sum tables cannot reduce to 0, 1 over k factorials, sum gamma 1, gamma k, the loops. But Ueltschi follows here, omega gamma I, gamma 1, omega gamma k. And then we still have all the sorry. Then we have this product x number, product I1 for 1 capital N, and this minus ji xx minus 2ix ax minus 1/2 minus mx I of gamma 1 gamma k. So I'm putting everything together because I suppose it's believable. So we have the exponential the sum of the loops. We of course we barely expand this, so we have the sum of the k, 1 over k factorials, and then we have the sum of a single loop raised to the k, which is really written as the sum, all both sums. And then we have all those factors over here. And here we use the fact that nx, I mean, when we have nx external gammas, we can regroup them into this nx of all these gammas. By the definition of these local times, the local time, in the time we sum over all the local times. And the 1/2 comes from the that's this thing over here, can check. That's why we get the extra 1/2 into the next subject here. But when we do that, I mean, the very last step, because you perhaps remember where we were. I mean, we are extending this z of a, there is still this Fourier modes. And the z of lambda, the one we are interested in, is basically the integration of this with respect to Fourier modes. So we still need to integrate this with respect to A. But no matter what, I mean, most things don't depend on A. Only this depends on A. And as you see, no matter what we get something which depends only on this NX. So here we have already seen the structure. Actually, it kind of proves it. We have not calculated what this function b is. But if we are just happy to check that we get the function only on local times, we have it here. Maybe I'm going to just make a few concluding remarks, but I'm not going to write any more equation. So I'm going to be a little bit fast with the other group here. But the point, I mean, well, we have this function over here. You remember this FD, but function FD that we have. This is exactly the Fourier transform that was on this form. And then you can write this interaction quite explicitly in terms of the convolution to this function. In the notes, I will give you further equations, including something quite explicit for this function V, so ratio of gamma functions. So when one looks at something more special cases, and when G becomes something explicit like this here at 1, one can make further simplifications. But otherwise, there is this thing that the function is this gas of loops. The weight of the loop is something quite natural. Every time you make a jump, you have the coupling constant, the corresponding coupling constant. The thing which is perhaps a bit less natural is this term over here, but it's fine. And yeah, and then we have Z. And in terms of the correlation function, well, you see what we get. I mean, we can do exactly the same expansion. The only difference is that with ZA, we also have this phi xi by yi, but we still get a Gaussian integral. We're going to use the second formula, which now I erased. But the second formula for Gaussian integration, I mean, about the moments. And then the expansions are quite similar. The expansion of this inverse of A gives the paths, and everything else is about loops. And again, at some point, you have to take a Fourier transform, so the inverse Fourier transform, and you get this thing about the interactions. Right, so I mean, I haven't given you all the details. I will write this down. I mean, if you're impatient, you can just look at the paper, which is for each answer. That's a good reference. Or the voice, okay. Yeah, I mean, very good reference. And that's it. So much more is already expected. I wanted to give you some additional flavors about this notching this and fundamental end work, but I mean, there are different ways of rewriting these loop expansions, including recognizing that we have a model of random heights, and that's where they make the connections with recent results of Slammers about delocalization, which can be translated back in terms of these slow decay correlation functions. And yeah, I mean, there are plenty of things to say, including various correlation inequalities. It's always nice to get monotonicity properties in all those business. And there is this sign lead and this inequalities, which are present in some cases, and altogether one can get the decayed transition. But the loops are kind of important. Maybe I'm going to stop now for today. Tomorrow, quantum spins. I'm not going to assume anything that we have seen today. Any additional questions? Good.
So is that already in the form that the semantic gave? So this so sorry, I rephrased it again. Did Freud spend to put it from semantic?
Yes, so semantic was looking at big theories, and he was looking into continuum, which is part why I mean, did think about this one of the organs is a mistake in the FS, I mean, which is for Spencer, but not in semantic. With this worry about having something exactly following its steps in the continuum is irrelevant. So the idea of Richard for Spencer was to use it for such a mechanism.
Okay.
And to get when they get these random walks instead of some kind of wrong version. Yeah.
So let me stop the recording.